Hi everyone, the origins of our universe have fascinated scientists and thinkers for centuries. The most widely accepted explanation is the Big Bang theory, which proposes that the universe began as an infinitely hot and dense point approximately 13.8 billion years ago. From this singularity, the universe expanded rapidly, giving rise to all the matter and energy we observe today. But what exactly happened in those early moments after the Big Bang? How did the universe evolve from a chaotic, energetic state into the structured cosmos we now see, filled with galaxies, stars, and planets? As we dive deeper into the story of the universe's beginnings, one of the most compelling aspects of the Big Bang theory is the strong evidence supporting it. Discovered in 1965, the cosmic microwave background is essentially the afterglow of the Big Bang, a faint heat that fills the entire universe. This radiation is a snapshot of the universe when it was just 380,000 years old, and it provides a crucial piece of the puzzle. The uniformity of the cosmic microwave background across the sky supports the idea that the universe began from a single hot, dense state. Next, we have Hubble's law, which describes the observation that galaxies are moving away from us in all directions. This redshift in light from distant galaxies shows that the universe is expanding, which implies that it was once much smaller and has been growing ever since. The farther away a galaxy is, the faster it appears to be receding. Strong evidence that the universe is expanding from an initial explosion. Finally, let's consider the abundance of light elements. According to the Big Bang theory, the early universe was hot enough to facilitate nuclear reactions that created the lightest elements: hydrogen, helium, and small amounts of lithium. The observed proportions of these elements throughout the universe match predictions made by the Big Bang nucleosynthesis model, further solidifying this theory as our best explanation for the universe's origins. Following the solid evidence for the Big Bang, the next phase of our journey takes us into the earliest moments of the universe, times so extreme that they push the boundaries of our understanding. First is the Planck era, the very first moment after the Big Bang, less than 10 to 43 seconds after the universe began. During this period, the universe was unimaginably hot and dense, and the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force were unified. The laws of physics, as we know them today, don't fully apply in this era, as quantum gravitational effects dominated. Scientists continue to investigate this period, hoping to unify quantum mechanics and general relativity through theories like string theory. Next, we move to the inflationary epoch, which occurred just fractions of a second after the Big Bang. In this phase, the universe underwent a rapid and exponential expansion, growing from subatomic to cosmic scales in a blink of an eye. This theory of cosmic inflation, proposed by physicist Alan Guth in the early 1980s, helped solve several problems in cosmology, such as the horizon problem and the flatness problem. Essentially, inflation smoothed out any irregularities in the early universe, leading to the uniform, large-scale structure we observe today. Following inflation, the universe entered the quark-gluon plasma phase, about 10 to 6 seconds after the Big Bang. The universe was still incredibly hot and dense, but as it expanded and cooled slightly, it reached a state where quarks and gluons, the building blocks of protons and neutrons, were free and not yet bound into particles. This quark-gluon plasma was a kind of primordial soup, and as the universe continued to cool, quarks combined to form protons and neutrons, which would later come together to form the nuclei of atoms. Experiments at particle colliders like the Large Hadron Collider have been able to recreate and study this quark-gluon plasma, giving us insights into the conditions of the early universe. As our understanding of the universe's early moments deepens, new theories have emerged that challenge and expand on the traditional Big Bang model. First is the multiverse theory, which suggests that our universe might be just one of many, an idea that radically changes our perspective on existence. According to this theory, what we perceive as the Big Bang could be just one of countless events occurring in a vast multiverse. Each universe within this multiverse could have different physical laws, constants, and even dimensions. The concept of a multiverse arises naturally from some interpretations of quantum mechanics and string theory, particularly in models like eternal inflation. In these models, inflation doesn't end everywhere at once. Instead, it ends in different regions at different times, creating pocket universes within an ever-expanding multiverse. Quantum fluctuations are tiny, random changes in energy that occur even in the emptiest space, according to the principles of quantum mechanics. During the early moments of the universe, these fluctuations were stretched to cosmic scales by inflation, seeding the formation of galaxies and large-scale structures. Essentially, the random nature of quantum mechanics played a crucial role in shaping the universe's structure. These fluctuations created slight variations in the density of matter, which, over billions of years, evolved into the galaxies, stars, and clusters we see today. With advancements in technology, such as the Planck satellite and the James Webb Space Telescope, scientists have made increasingly precise measurements of the cosmic microwave background radiation and the distribution of galaxies. These observations have provided new insights into the universe's rate of expansion, the nature of dark matter and dark energy, and the conditions in the earliest moments after the Big Bang. For example, the Planck satellite's data has allowed for more accurate measurements of the universe's age, composition, and geometry, refining our understanding of its evolution. In modern cosmology, the Big Bang theory not only explains the universe's beginnings, but also serves as a foundation for understanding the large-scale structure of the cosmos. The theory's implications reach far beyond the moment of creation, influencing our comprehension of the universe's past, present, and future. The idea that the universe is expanding, for instance, has led to crucial concepts such as Hubble's law and the cosmological redshift, which have been instrumental in measuring the rate of this expansion. This, in turn, has provided insights into the age of the universe, estimated at approximately 13.8 billion years. Whether the universe will continue expanding indefinitely, eventually slow down and collapse, or reach a steady state depends on factors like the density of matter and the mysterious dark energy that accelerates expansion. These models are fundamental to our understanding of cosmic evolution and the future scenarios that might unfold. The Big Bang theory has also profoundly impacted our understanding of the universe's composition. It has led to the discovery and study of dark matter and dark energy, which together make up about 95% of the universe's total mass energy content. While these components remain largely mysterious, their existence was inferred through observations rooted in Big Bang cosmology, such as the rotation curves of galaxies and the accelerated expansion of the universe. In addition, the theory has influenced the way we think about time and space. The notion that space itself has been expanding since the Big Bang challenges the classical view of a static, eternal universe and introduces a dynamic, ever-changing cosmos. This has profound implications for the way we perceive our place in the universe, suggesting that everything from galaxies to atoms has evolved from a common origin. Looking forward, the Big Bang theory continues to inspire and guide future research. Upcoming and ongoing missions like the James Webb Space Telescope and next-generation gravitational wave detectors aim to explore the universe in greater detail than ever before. These tools will allow scientists to peer further back in time, potentially observing the first stars and galaxies that formed after the Big Bang, and to study phenomena like cosmic inflation and black hole formation with unprecedented precision. The ongoing exploration of the universe, driven by advanced technologies and innovative theories, promises to reveal even more about the early moments after the Big Bang and the forces that continue to shape the cosmos. As we push the boundaries of our knowledge, we are reminded that the universe is a dynamic and ever-evolving entity filled with mysteries yet to be uncovered. In essence, the story of the Big Bang is far from complete. It is an ongoing narrative that continues to inspire scientists, challenge our understanding, and reveal the deep connections between the universe's origins and its ultimate destiny. As we continue to explore and discover, we contribute to the ever-growing tapestry of knowledge that defines our understanding of the universe and our place within it. The journey is ongoing, and the future holds the promise of even greater insights into the cosmos.